Okay, this is our last section out of the textbook, 8.8, Numerical Integration. And you have seen almost all that we're going to talk about today other than the midpoint rule. So, why do we need these numerical integration techniques? Actually, this was the way this calculus was figured out before the antiderivative and definite integrals. All right? And it is still used because we cannot find the antiderivative of every function. So with that, then, we have to be able to have some good numerical techniques to do so. So numerical integration is the process of approximating a definite integral using well-chosen sums of function values. It is needed when we cannot find an antiderivative explicitly, as in the case of the Gaussian function, which you guys know better as the bell curve. And that function is, remember that, e to the negative x squared over 2 power? Right there. There's no antiderivative. We cannot find that function, so we must use numerical integration. To approximate the definite integral, the integral from a to b of f of x dx, what do we do right here? Well, we know how to do that, but unfortunately now, we don't have an antiderivative of this function, so we've got to use our numerical stuff. We fix a whole number n and divide the closed interval from a to b into n subintervals of length, and here's the key. Delta x, you guys already know this, is always b minus a over n. The endpoints of the subintervals are, well, x sub 0 would be my left endpoint a, x sub n would be my right subinterval b, right endpoint, and then x sub 1, of course, and all I'm going to do is add delta x every time. So a plus delta x, a plus 2 delta x, and so on until we end up with that a plus n delta x, or b. We shall denote the values of f of x at these endpoints by y sub j. So, y of 2 equals f of x sub 2, which equals, and here we're going to go right here. See that x sub 2 right there? A plus 2 delta x. So that's just f of a, my left endpoint, plus 2 times my delta x. Okay. So let's say that would be that point right there. Okay. Now, y sub j equals f of x sub j, which equals f of, all right, well, we always got to start at a, plus, and that would be then simply a j times delta x right there. So there it is in general right there. This makes it look way more complicated than it really is, as you guys will see. In particular, y sub 0 equals f of a, and y sub n equals f of the b right there. Okay, trap rule. Now, I've introduced to you guys the trap rule. We didn't use it a lot. You're going to use it a lot now, okay? And we mainly did the trap rule with the right endpoint and left endpoint approximations, where we use the average, or we would find the area of each individual trapezoid in the subinterval, and both of those ways work 100% of the time. So, trap rule, all we're going to do is find the area under this curve with all of these trapezoids right there. And look, that looks pretty accurate, doesn't it? So, here it is right here. The nth trapezoidal approximation to the definite integral of a from a to b of f of x dx is, all right, now remember we go 1/2 of our delta x when we're using a trapezoid, all right, and then we've got to have our left endpoint with the output, right, and then we go 2 times every other one. 2 times y sub 1 plus 2 times y sub 2 plus 2 times y sub 3 until we get to that 2 times y sub n minus 1 right there. There's my trapezoid rule. Where delta x is, one more time, that's right, b minus a over n. And y sub j equals f of my left endpoint a plus the j delta x right there. Conceptual insight. We see that the area of the jth trapezoid, that would be this dark region right there, is equal to the average of the areas of the endpoint rectangles with heights y sub j minus 1 and y sub j. And that's why we had the method where we took the average of the left endpoint and right endpoint approximations. So it follows that T sub n is equal to the average of the right and left endpoint approximations R sub n and L sub n introduced in section 5.1, and we have done this. So T sub n equals 1/2 of R sub n plus L sub n right there. In general, this average is a better approximation than either R sub n alone or L sub n alone. And we may need this when asked to use a trap rule when our delta x is not constant. You've seen that before, and you're going to see it right here on our first example. So use a trapezoidal sum to approximate the definite integral from 1 to 10 of f of x dx, where f has the given values. And notice here, look at these delta x's. I go 3, then I go 2, then I go 3, then I go 1. I can't use the trap rule. This won't work because I do not have a constant delta x. So we can find the sum of the areas of the trapezoids or take the average of L sub n and R sub n. I kind of like doing the average. It's pretty straightforward. So let's start this off here, okay? The definite integral from 1 to 10 of f of x dx is approximately t sub, and now I need to know how many sub-intervals does this table give me? 1, 2, 3, 4. T sub 4, okay? And that's going to be then 1/2 of my left endpoint approximation plus my right endpoint approximation right there, just like that. All right, so let's find L sub 4 really quick. Now, L sub 4, all right? Well, here's what I'm doing. My output is 7, and my delta x here is 3. So picture the rectangle, height of 7, base of 3, 21. Then I go height of 2, base of 2, 4. Then I'm going to go height of -1, base of 3, -3. And then I'm going to go height of 3, base of 1, +3. And that looks like a 25 to me. So I'm going to say this equals 1/2 of 25. And now all I have to do is the same thing to find my R sub 4. And R sub 4 would equal, now, 2 times the 3, 6. Oh, don't hit that button there. There we go. Sorry about that. That's a 6. All right. -1 times the 2, that's a -2. 3 times the 3 is a 9. And 5 times the 1 is a 5. And I've got, what, a 4 plus 9 is 13 plus 5, 18. So guess what? The trapezoid rule is equivalent to 1/2 of 25 plus 18, which is 21.5. There you go. You've done that before. Pretty easy, isn't it? Okay? Now, let's take a look at the midpoint rule. The nth midpoint approximation to the definite integral from a to b of f of x dx is, and you have not seen this one before, m sub n. I've got a delta x, all right? And then I've just got to have the inputs at each midpoint of my subintervals. So we do this f of c sub 1 plus all the way to f of c sub n, and then everything in between, f of c sub 2 and so on. Where delta x is, one more time, you guys know it, b minus a over n, and c sub j would be a plus, now remember on the trapezoid rule it's a plus j delta x. We're talking midpoints now. Instead of j delta x, it's j minus 1 delta, j minus 1/2 delta x is the midpoint of, and then it's just got to be one of my subintervals. So I'll call that x sub j minus 1 to x sub j. There we go. Makes this look way more complicated than it is. Wait till I show you it. Okay, so graphical insight. M sub n has a second interpretation as the sum of the areas of the tangential trapezoids, that is, trapezoids whose top edges are tangent to the graph of f of x at the midpoint cj. tangent right there, just like that. The trapezoids have the same area as the rectangles because the top edge of the trapezoid passes through the midpoint of the top edge of the rectangle. And the rectangle and the trapezoid have the same area there. Do you agree with that? Okay. So here we go. M sub n is the sum of the areas of the midpoint rectangles. M sub n is also the sum of the areas of the tangential trapezoids. Like that. So those two are equivalent, believe it or not. Okay, so here's what you're going to be able to walk out of here and have to be able to do. I see at least one test question that looks almost just like this. I'll just have to change that function, huh? So let's find t sub 6. That's the trapezoid with 6 subintervals, or midpoint with 6 subintervals right there. So let's write down our general again. And you start a problem, write down the formula you're going to use. So don't we go 1/2 delta x? All right. And then we've got our left output and our right output. Y sub 0 plus y sub n. And then all the other outputs we've got to multiply by 2. Okay. And I'm sorry, but my sheepadoodle is right in the middle of my screen right now wanting some attention. Hey, Maggie, I'm recording a video for my calculus students right now. Okay. I wish you guys could see her. She's so cute. Okay. She's worried about me too, but I'm getting better every day. Hey, you can be up here, but you need to lay down, okay? Yes, I'm teaching from the bedroom again. Okay, so M sub n. All right, that's just a delta x out front right there. And then we've got our f of c sub 1 all the way to our f of c sub n. Okay, so delta x, well, you guys all see b minus a would be 3. N is 6, 3 over 6, 1/2. Calculator. Now, here's what I'm going to do on my calculator. So do this very carefully. Okay? I'm going to just put the square root of x in as my y sub 1. And then I'm going to set up my table to have my key outputs. Because think about what I'm going to need here. I'm going to need a 1. And then what am I going to need? My 2 times the y sub 1. So watch how I set this up. So I went 1. And then I end up at 4. And you see my delta x right there? 0.52, 2.53, 3.5, and 4. Right on. Now, this is only the outputs of the square root of each of these numbers right here. So we're going to take and we're going to put these into this set of parentheses right here. And then we're going to multiply by 1/2 times 1/2 or 1/4. So if you do that very carefully, and you guys need to take a moment and do this on your calculator and make sure you agree, you're going to get 4.661. Simple, simple, simple. Okay? Now, C sub j equals a plus j minus 1/2 delta x if we're going to do the midpoint. But you guys, I don't ever think about this because I know exactly, just by looking at my trapezoid rule, what my midpoints are going to be. Okay? Hey, what's the midpoint of 1 and 1.5? 1.25. What's my delta x? 0.5. So I'm going to go 1.75. 2.25, 2.75, 3.25, 3.75. Now I'm going to set up this table. And of course my screen shows a little more than I need. So let's cross out that last one so we don't accidentally use it. And there it is right there. So I'm going to take these outputs. I'm going to add them all together and multiply by 1/2. And if I do that, I get 4.669. You guys make sure you do that. Okay? And that looks like a pretty easy test question to me. You're just crunching numbers. How close are we? Are you guys curious? Well, let's see. Let's do it regular here. So I got what? X to the 3/2 over 3/2 multiplied by 2/3. And that's going to equal, fundamental theorem of calculus now, I've got square root of 4 is 2 to the 3rd power. That'd be an 8. Square root of 1 is 1 to the 3rd power. That's a 1. So I see a 14 over 3. Okay, well, gosh, I'd like the decimal here. So 3 goes in the 14 4 times. That's 4 2/3. What do you guys think? 4 2/3. Pretty close, huh? Okay, here's your problems. And again, for 1, 7, 11, just do those numerically. All right. And 23, I guess they'll let you do whatever you want. No, 23 and 27 use trapezoids. And for number 28, use midpoints. All right. You guys have fun with these problems. And next thing I'll do is I'll get you a review for this test. Okay. So everybody have a wonderful day.